Everyone, please. Good morning, everyone. Uh, Today I'm going to give a presentation on Elasticsearch, and I will describe how it is used, why it is used, and everything about that. So, before beginning the presentation, I would like to have few disclaimers. The first one is I am not an expert on Elasticsearch. I have studied it, and from the last few days I have been preparing it. So whatever I have studied or gathered, acquired knowledge, I'll try to present with the best possible knowledge I have. And the second thing is, during the presentation, you might have questions and doubts. So please note them down for a while. And since this presentation is long, a little long, and I'm going to cover so many topics, so I'll address each one of them at the end of the presentation. So let's begin. So let me give you a brief outline of the presentation, what I will be covering. The first, it is divided into 5 sections. The first is the introduction and overview regarding what is Elasticsearch, how we can use it, how we can install, run, and how we can communicate with that. The second one is starting Elasticsearch. So uh, I'll show you practically, and we will run some queries, searches, analytics on that. And the last 3 points are really important, and because the first two in these queries and API, you can look at uh, the options on Elastic's website. The official website is elastic.co. But the last 3 points, knowing the technicalities, in which I will try to explain how uh, Elasticsearch operates in a clustered and distributed environment. And in fourth point, I will explain how cluster changes state when a node is added, when a node is deleted, and how they communicate. And the last point is really interesting, how distributed search works. So let's begin. So the first one is, what is Elasticsearch? So Elasticsearch is a distributed, highly scalable, open source, full text search and analysis engine. So for a naive user, for a user like me who does not know anything about Elasticsearch, Elasticsearch is a search engine which works on top of Lucene. Lucene is another Apache project which was introduced some times back, and it is on top of that. It is like a wrapper of Lucene. And when I say distributed, it is distributed from ground up. When you install Elasticsearch and when you run, it is by default clustered. It will have only one node, that is your machine's node, but it is by default clustered. If you start any node on a different machine, they will form cluster. I will explain later how they form. So it is highly scalable. Scalability. When we talk about scalability, the first one is scaling up. That you want to scale your application up, you add resources like more processing power, more memories too. But it has its own limitations, because after some time you are not able to add, because it has limitations, physical limitations. But the second type of scaling is scaling out, which is like adding nodes or adding runtime systems at runtime. So this type of scaling is infinite, and in distributed environment, this type of scaling is done basically. So it is open source, it is under Apache license, so anybody can look at the source, how they perform. It is full text search and analysis engine. When I say full text search, means when you index, when you try to search in a field, like we search in a database, we like contains query or something like that. So how database does that? It searches each and every record for that, but it's a different mechanism of in Elasticsearch. Full text search means it will try to pick words, individual words, and map documents as per words. Like this word is mapped into these many documents, like that. I'll explain it further. And it allows to store, search, and analyze big volumes of data quickly and in near real time. So yes, it is pretty much like that. And when they say near real time, it means it's not real time. When you when you store a document, you give a document to Elasticsearch and you try to search at the same time from a different node, it will not be accessible because it's a distributed system. It can have multiple nodes. So the documents need to be replicated to the replica nodes, which have been configured into that. So it takes a little amount of time for that. Okay, so it yes, it also depends. It also depends on how many replica nodes you want to store your data. Like if you have more replica nodes, it will take more time. Okay. So it is basically used for these things. Structured search, like when our data has some inherent structure, like it follows, like we say an employee object. A full text search is like when our data is not structured or semi-structured or unstructured, like email messages or other things. And the analytics is like performing various types of aggregations on the data. And why Elasticsearch? The basic question, which I had in my mind also when I started studying for this. So there are several points. The first one is it is extremely fast. I have not mentioned it here, but it is extremely fast. Let me cite you an example. I mean, it's officially not in Elastic website, but I've read it somewhere that a person has indexed entire Wikipedia into its search clusters, and when he tried to search stuffs from that, the results were coming in milliseconds, and you can understand the volume of data contained in Wikipedia. So the first advantage is, or let's say the reasons why we should use Elasticsearch is it is schema free. If you want to like you have an employee object, for example, a simple employee object, and you want to store and search data. So while storing data into Elasticsearch, it does not ask you for schema. That you can simply store that object and it will intelligently guess the types from the data you have provided, that okay, this is a string, this should be a textual data, this is a number, this should be inside number fields. So it is schema free, but that does not mean it is schema less. It has mappings. For better performance, we have to do some mappings with those data types which are provided by Elasticsearch. And there are several data types supported by Elasticsearch, like all the common primitive data types. Apart from that, it supports spatial data, that is geo point, geo shape, binary data it provides supports. It supports objects, nested data types, arrays, and IP, and several others, which are commonly used in web domain. The second is the support of unstructured data. Your data can have any structure. I mean, Elasticsearch does not let you restrict your data structure. I mean, it does not bother what your data structure is. You can have one structure for one data type, one employee object. A second employee object can have different kind of structure. It can have additional fields or not. So it does not matter to Elasticsearch. I mean, like in RDBMS, it is very complicated to do this thing. And the first point is also very complicated. Impossible in RDBMS systems. The third point is analytics. It is able to perform several kinds of aggregations on data, several different kinds that I will take up later. Synonyms. You can search data based on synonym. Like if a word has multiple meanings and you try to search a word and those synonyms are registered, indexed into Elasticsearch, it can find synonyms of those documents also. This is a feature. The next feature is relevance. The concept of relevance is very important in Elasticsearch, and it is completely foreign to RDBMS systems. Like in RDBMS, whether a record matches or not matches, it's like that only. But in Elasticsearch, it can show you how well how well a keyword matches to the documents by giving a score, a relevance score. And documents are indexed in that order. The most matched documents are at the top, and the least matched documents are at the end. And the next point is simple API. It is a very simple API. It is universal. It has chosen universal API. It supports. It has RESTful APIs which adhere to the REST architectural style. So you can, with your favorite browser, you can access it. And REST on top. And JSON is the data exchange format, which is nowadays very popular in web technologies. And the next is fuzzy search. It is also able to do fuzzy search. When I say fuzzy search, it means minor mistakes can also be corrected using Elasticsearch, and can search document. Like if it is jump and you search jumped, it is also possible. The next one is auto completion. It can automatically suggest you data when you type and search based on its operations. And the next one is search result highlight. When you search, you can also define the result terms which included keyword matches should be highlighted. Okay, the next point, who uses Elasticsearch? So this is the list basically. So the first one is Wikipedia. Wikipedia uses it for full text search and highlighted search snippets, and it is also using it for search as you type. And did you mean suggestions also? The second one is Stack Overflow, as we all know. It also uses it for full text search along with geolocation queries, like from which location this question has been asked most, and more like this to find answer. Like when you try to ask a question in Stack Overflow, it gives you a list of questions. Many of us know. So that is due to the Elasticsearch. It finds if these questions have been asked earlier, so that you don't type a new one. GitHub uses Elasticsearch to query its entire 130 billion lines of code base, and the results are in milliseconds. Facebook uses it as a managed service, and there are others like Quora, Netflix, The Guardian, Adobe Systems, and Mozilla. And listed so much on its wiki page. So how it all started? So the creation of Elasticsearch is done by this gentleman, Shah Benon. So once upon a time when Shah was unemployed and his wife was studying to be a chef, they moved to London, and Shah started playing with Lucene, Apache Lucene, and at the same time he wanted to make her wife a search recipe engine kind of things. She used to find it difficult from internet to find those things. So with Lucene, he found it very complicated in using, because Lucene has its own science in information text retrieval. If you have studied a little about text retrievals and its algorithms like edit distance and grammar, vector space like things, so it is complicated, little complicated, and you need to understand. And Lucene is something which needs a thorough background. You need to understand how it works. So he wanted to make it simpler, so he created an abstraction level layer of Java, so that end users should not bother about those technicalities. They can simply search, index, or whatever they want to do with Lucene with a familiar syntax and easy syntax. So the first product he created was known as Compass. And then later on, when he joined another company, but that company was totally based on distributed architecture. So it has in-memory grids, and it was the systems where all those services or systems were distributed, and Compass failed miserably in that. It was not able to perform. So he decided to write it, develop it from ground up as a distributed system. So the result is Elasticsearch, and the first version was released in I think 2010, and from there now it has become widely accepted and the de facto standard for searching and analytics operations. Though now we as end user developers, how we can use Elasticsearch. So before starting Elasticsearch, the only requirement is that Java should be installed on your machine, and you can check that. And once you have Java installed, you can go to this website elastic.co/downloads, and you can download the zip file. It is once you download, and you can put it in any directory. It is accessible, and let me show you. I have downloaded this Elasticsearch and extracted it to C drive. So it has several folders, but the important folders are config and bin. So in bin folder, it is having files which would run your Elasticsearch cluster. And for Linux environments, shell scripts would be there, and for Windows, the batch file is there. So elasticsearch.bat is the file you want to run. And in config, there is a configuration file, YML file. I hope you are aware of this YML standards. So this, if you don't do any configuration, by default, it runs on localhost and with the cluster name Elasticsearch. But I have modified it, and I have created a 2-node cluster. There are 2 machines which are running, and I have modified a little bit. So I'll show you later. So running, I already told you that using the BAT file. So by default, Elasticsearch uses port 9200 to provide access to its REST API. And this port is also configurable if you want to do. So by default, if you anything, if you can hit from browser localhost /9200, it will give you cluster information. But sometimes it is not possible from browser to, it is for get request it is fine, but for put post delete you need a client, you need a REST client. So for that I initially tried to do using Postman, but then I became aware about a tool that is already provided by Elasticsearch community, and that is Sense. I'll show you that later. And okay, let me show you first. So it is a visualization tool. Actually, Elasticsearch has several plugins and tools for different things. So Elasticsearch is like for search and indexing. So there is a Kibana. Kibana is used for visualization stuffs, like you want your charts, diagrams, your pictorial representation of data. And there is another one like Logstash, which will let you analyze logs in your web application or systems, where logging is very common. So if you want to analyze who logs into which location, from which location, which IP, to which action is frequently accessed, less accessed, that kind of thing. So Sense is provided as a Kibana component. So I have also installed Kibana in that. So it by default runs on 5600, and this is the view of this. And see, the any one node is required for communicating to the cluster. So I have two nodes. My node I have given in server address, and on port 9200 it is running. So I am just giving a simple REST command, that is cat nodes v. I want to see my cluster information, like how many nodes are there. So there are two nodes. The one is of Sagar node and Udit node. These names I have configured in the respective YML files. Okay, let me show you YML files a little. So this is the Elasticsearch YML file, and the first one, configurable property, is cluster name. If you don't configure, it will Elasticsearch by default. So I've configured it as Udit cluster. The node.name is another property where you can define configurable names for those nodes. And I have made this node as master node. So in Elasticsearch, there are different kinds of nodes, and different responsibilities are assigned to those nodes. So one is, this is my master node, and it is a coordinating node, which is also a data node. And node.data equal to true. If you will do, it will hold data. If you don't do, it won't hold data. And it will act only as managing the cluster operations. So other things are like network host bind parameters. If you don't do anything of this, that can also okay, but we did it as we were trying to establish a cluster communication. The HTTP port is 9200 by default, and transport port is required by default. And we don't need to provide it. The second two important things are like Zen ping unicast host. So for network communication, it uses unicasting in place of multicasting. Because in multicasting, every node's multicast, and they try to form a cluster. For example, suppose your production and testing environments are both, and if you have not configured names, so it might happen that accidentally your production nodes can join with your testing servers nodes, and your data will be mashed up. So this is using unicast, and in unicast dedicated nodes can be provided, so that if I have given this Sagar's node address, so when I will boot up, I'll try to establish communication with that node. So that is the main purpose of this. And this is another parameter, gen.minimum master nodes. That is a different thing. I'll explain you later why this is needed. Okay. So now let's try to understand. Now we have installed Elasticsearch. We have started. It is running on port 9200. Now how we can talk to Elasticsearch? So since it has been developed in Java, so it should compulsorily provide support for Java, I think so. So it has support for Java, and it has two built-in clients. Like you can use, you can download those ZAR files, and it has clients like node clients and transport clients that I'm going to explain in the next slide. And for rest of the community, apart from Java, they can access Elasticsearch using those RESTful APIs as a REST service. Okay, so next, The next one is about node client and transport client. Why we should use node client and why we should use transport client, and what is the difference? So node client is used in environment when your Elasticsearch cluster is on those same platforms on where application is running. So it joins locally that cluster, and it is aware, that system is aware, like your application has node client integrated into it. Your application becomes aware of the distribution, aware of the indexes. Like in Elasticsearch, all nodes are aware about each other, like how indices are stored on different nodes. Every node is aware. So this is something which is managed by Elasticsearch. So if you use a node client, your node is aware. So when you search for an index, it knows exactly where to go and pick documents. But it has its own overhead, like you have to have additional jars for that. And the second communication mode is when your Elasticsearch cluster is not hosted locally. Like suppose it is on Amazon's cloud or a different cloud service. So you can communicate with that cluster using transport client. So in that, your client is not aware about distribution. It will just submit the search request to one of the nodes of those cluster, and then those nodes will communicate and give result back. So it has advantages of having less jar, less dependency, but additional network hops. Okay, now the important thing is both the Java clients, node client or transport client, how they communicate with Elasticsearch on which port, since 9200 is used for REST clients. So for 9300, the port 9300 is used for these Java clients. So they communicate on that port. And intra-cluster communication, the communication among nodes is also performed using this port. So if that port is not open, your nodes will not be able to form cluster, and you will not be able to access them. So there's a difference in Elasticsearch and the basic RDBMS systems, the way data has been organized into this. So it does not look into data like the way it does, or they enforces us to store our data, because they have simple row and columnar structures. So sometimes what happens that, like if your object has so many objects, what is objects? Objects give you flexibility to add data to that, but that flexibility is restricted by relational database management systems, because they are not simply able to represent all those flexibilities, because they have a rigid structure. They want that to be conformed into rigid structure. And if you want to have a, they have a rigid structure, and for complexity you have to add additional tables, and you have to do normalization and stuff like that. So it makes your data a little complicated to query. So Elasticsearch does not take into account in all this. It views everything as a document. So whatever you do in Elasticsearch is a document. You store a document, you retrieve a document, you search a document, you sort a document, you filter a document. So this is a different way of thinking from RDBMS, a different altogether way. And that is the way, this is the default way nowadays. NoSQL databases and all those things are in the market, and they work on those concepts only. So important thing, like in RDBMS we have indices, like we want for faster execution of our requests. Sorry, in RDBMS, yeah. If we want our data, we create indexes for faster execution to pick records. So index is the word which is overloaded here. So when I say an index in Elasticsearch, it is like similar to a database in RDBMS systems. So whatever you create inside an index. And the term is overloaded. So when we say we are indexing something, means we are storing something. And index as a noun is a database in Elasticsearch, and when we are indexing, we are storing something. And the third one is the inverted index. It is exactly same as the RDBMS things, but it has its own mechanism of handling things. So that I'll explain later. So now let's see how we can use Elasticsearch. So my system is running. As I have shown you, we have two nodes. So let's index a document. Let's store a document. Let's save that document to Elasticsearch cluster. So the act of storing data is known as indexing, as we know right now. And so we can have multiple indices, and every index contains types. So index and then types, and then those types will contain your data, your IDs. Like for example, if we want to index an employee object of an IBST employee, we want to index it to Elasticsearch. So first we have to create an index like IBST. The rest verb. So since it is already on based on rest, so if you will see, if you look at the request, the last one I showed you on website, it was get verb, it is put verb. So it completely adheres to the REST architectural style. It is everything in that. And the data which is provided is JSON. So JSONs in these fields are there, these are fields. So if I'll copy this thing and if I'll paste it into my Kibana, it will index this employee object and it will give me a message that if it has been indexed or not. So let's do this. Okay, and let me do this. So you see the information which has been retrieved. So index with this name, IBST, type is employee, ID is 1, version is 7, because I have, for testing purposes, I had created several times employee object and later on I deleted it. Shards are conceptually things in distributed systems that I will take up later. So there are total two shards successful, and created is equal to false because it is already there, I guess. Yeah. So let me try to get this. If it is there, okay. So it is already there. We just change the rest verb and we retrieve the employee object. So it has information found is equal to true, and you can see the source field. The source field contains exactly the data you have submitted to Elasticsearch. So it has no manipulations in data, and the rest are metadata fields like which type to the document belongs, what is the ID, what is the version, and other thing. If it does not found, like if I write non-existing ID, it will say found equal to false, and source field will not come. So, okay. So okay, shift. So since we have retrieved, now simple search is how we can search. So simple searches are known as search light in Elasticsearch. It is based on query string format. We can write append q, and then we can have the field names and the value names which we want to search. And if you want multiple fields, they can be separated by space. And if you want that this field must match, they can be prepended by a plus symbol. If you want that it must not match, they can be prepared by minus symbol. And if you want multiple values, they can be inside parentheses. But since it's a query string format and it requires special characters, so sometimes it becomes, it looks like really creepy, and its terseness make it difficult to search. So for that, this Elasticsearch has a very good solution, and that is known as Search DSL. And Search Lite is not recommended for production. It is used for ad hoc queries, like you are in the process of using, and you can search quickly like, okay, this exists, this does not exist. So query DSL is something which is very rich, flexible. It has its own query language, and it provides you a mechanism to add several things, like several different things. Imagine if you have 20 fields and you want to search on the combination of 20 fields, how will it look in query string using Searchlight? So for that, it is little verbose, but it is very meaningful and understandable. So first, let us do this search. Uh, okay. Okay. Control C. So the first one, without any query string parameters, if we will do this, it will search everything inside that index. So it will give me everything, and the things which will come inside hits array, like how many records have been matched, and then it will have those record details in hit array, first record, second record, and the inside that hit this is for same, the JSON is same as we were in getting single record. So like now we want to search. Uh, okay, last name. Okay. Okay, I made some mistake. Okay, so now we know that it is case sensitive. Okay, so this is the search result. And can you record will not match, but uh, query I can show you. This is like this. So the match expression is already there, but we have prepended it with a must match, that record must match with last name of Mishra. And then we have appended a filter like age should be greater than 30. So in this way that it can be done. Do you want me to perform this in ElasticSearch? Okay. Okay. Now full text search. So what actually is a full text search? When we say full text search, it is like when I studied, it was alien. The concept was alien to me. Like in full text search, in Elasticsearch terminology, full text search is like if you have document, and if your record contains like 1,000 words, and you want to search up for a particular word within that documents. So Elasticsearch creates inverted index for those fields, and when you search for a document, those inverted index, those words will be matched according to the documents. The whole process is like this, like you have 1,000 words, okay? So it will first try to, it will separate all individual words and it will store them into a data structure. Then it will apply a lowercase filter to make it case insensitive. And then it applies stop word filters. Stop word filter is like when we have documents, we have like stop words and or which are not meaningful. So it removes them. And then it provides stemmer. Stemmer is also a concept where we have, suppose words meanings are same but they are in different tenses, like we have jump and jumped. So it normalizes those keywords, and then for each single keyword it matches a list of documents, like keyword 1 is word 1 is matching to doc 1, doc 2, doc 3. So these document list of these doc IDs will be associated with that word. So when we search for a particular keyword, that can be retrieved very fast. Unlike in RDBMS systems, like in RDBMS, what do? Like we search each and every field for contains. So it is already written, and this I have copied from Elasticsearch website. This concept of relevance is important to Elasticsearch, and is a concept that is completely foreign to traditional database systems. And it also stores relevance scores for matching documents. So full text search is, you might be wondering that it is same as the first search. So full text search takes into account field type. So if your field type, the data type, which I have not discussed, which I have discussed in brief. So if your data type is text, it will perform a full text search. If your data type is keyword, in text we have two variations, text and keyword. If your data type is keyword, it will perform exact search. It will not taken into account relevance, score and other things. It will behave like RDBMS systems, like matches or not matches, like this. But if your data type is full text search, it will give you a relevance score. So this we will see in example. Because I have records which are more relevant and less relevant. So I want to convey that. Control A. Okay. So let me just remove climbing. Okay. Control V. Okay. Let me search this. Okay. So when I search for only a keyword called rock, I have two documents because in about field, like in my record, I like to collect rock albums, and in Shiv record, two records, the one is of Shiv, one is of mine, and in both the about fields, rock is there. So when I search, their score is same, like 0.115. But when I search rock climbing, it will let me know that this document is more relevant than another document. And another document does not go away. It will also come in the search request. So you can see when I say rock climbing, my record comes up than Shiv's record, and I have a better score than his record. So this is the concept of relevance in Elasticsearch. Okay, the second one is analytics. Elasticsearch can perform multiple types of aggregations. Like in RDBMS systems, we have aggregation, group by clause, having clause, but they have their own limitations. After certain extent, you are not able to perform, or it will take more efforts to write a complicated query, but that is not the case in Elasticsearch. The aggregations are very simple, and they can be combined, and they can be used as a pipeline for other aggregations. So basically, this is one simple example of aggregations. Like we are searching for employees, we got 3 employees suppose, and then we will group them by interests, like whose interest, we will count employees by interest. So if I'll run this query, I'll have like 2 employees in music and other things. So this is a type of bucket aggregation. Elasticsearch basically supports, I think, 4 type of aggregations. The first one is metric aggregation, in which we have normal functions like count, min, max, average, and other things. The second one is bucketing, in which like we have popular terms aggregation, significant terms aggregations, dates aggregation, and the next one is pipeline aggregation, in which data will not be searched. The result of an aggregation can be provided as a pipeline to another aggregation. And then we have metrics aggregation. Metrics does 7 to 8 aggregations at once and give it for a numerical field. So if you want all possible combination of aggregations, you can use metrics aggregation. It is like fields like standard deviation, correlation, and other things. So there are several examples on elastic.co website if you will refer later, and I hope so you will refer. So it is very flexible. So I have covered this basic aggregation. If you want me, I can show this to you, but let me show you how we can further aggregate the aggregated data. So okay, I will run this. So let's say we are aggregating on employees like interest, group them by interest count, and then we will further aggregate, like suppose 2 employees come under music. So if music in their interest field, and we want to find averages of those 2 employees, averages of those employees which fall under particular category. So we can do like this, the further aggregation. Okay, let me show you. Okay, so first it will give you the documents which matched in hits array that I explained earlier, and now this is the aggregation. The field which I have named, I have given that user-defined, user-friendly name all interest, And then it will, as I mentioned, it is a bucket kind of aggregation, so it has bucket. So music, we have two doc counts, and the average age of employees which are in music is 28.5. In chess, there is one document, and forestry also there is one document, and average age is there. So this way we can have any possible combinations of aggregations, and it is really flexible. So, okay. So that was all about, we knew how to install, run, use aggregations. Now these topics are really important, knowing the technicalities. So what actually is Elasticsearch? So under the hood, it is Lucene engine. Lucene project was developed, and it is on top of that. It internally uses Lucene ZARs and makes call to them. Lucene is extremely fast in information retrieval and searching purposes. So it is using that, and it is just like wrapping it so that it is very useful to us. And since Lucene's syntax is really difficult to understand and to use. So this is an architecture of an Elasticsearch cluster. So it is clustered from ground up. As I said, if you start one node, it is clustered. And if another node will start, they will communicate using what they can say, I think, is a gossip protocol. It is basically used in distributed environments. So using that protocol, they communicate, and with the nodes given in gen.unicast addresses, and they will form a cluster. So now I will explain what actually is a cluster, what are nodes, what are shards, what are replicas. So cluster can be distributed and can be highly distributed. Like if you put your entire Elasticsearch cluster on EC2 or on Google Clouds, you can have infinite scaling, as many nodes as you can want. And these nodes can be added at runtime. You don't need to put your cluster down. They are accommodated at runtime, and the cluster reorganizes or rebalances itself. Okay, so what actually is cluster? So it's a set of nodes running together, and it gives a coherent view to us like a single system. But internally, several systems are distributing their performance loads, their workloads, as well as data. So they collaboratively, they achieve high availability. When I say high availability, means it is highly available. If you see from Kibana, for example, visualization tool, that your Elasticsearch usage has reached to 80%, you can add nodes at runtime. You can also create filters on that. It can notify you that your cluster usage has reached to this point. So it is highly available. And scalability. Scalability, as I explained earlier, horizontal scaling. And second one is load balancing. It distributes the load. So when you search for any keyword, the search is propagated to all the nodes which are having pieces of data or under that particular index, under that type. And then that data is accumulated and given back to the client. That I'll explain later. And fault tolerance. It does not matter if 2 of your node goes down or 10 of your node goes down. As long as you replicate your data with a good amount of threshold, like you have 1 copy of data as a primary copy, and you can have 10 copies, depending on it. It is all relative to the cluster size and data size. So nodes are added, removed from cluster, and it organizes itself. So what actually is a node? So node is a running instance of Elasticsearch. And whenever I hit that elasticsearch.bat file, a node is start. A JVM process actually starts, and the node Elasticsearch runs on top of that. And we have a cluster of 1 node. If I start a node, if I start second node, we'll have a cluster of 2 nodes like we have right now. And the important thing is that every node is aware about every other node. So Elasticsearch cluster nodes are distribution aware. They know how many nodes are there in the cluster. They know this index, this data is stored in these many nodes, these way. So when a search request is fired, it does not look into its table. It does not, it knows where the data is. It redirects queries to those data. So nodes are of several types depending upon their usage. So the first one is master node, and the entire Elasticsearch can have only 1 master node. although it can have multiple master eligible nodes, but master node is only one, and that is basically used for managing the cluster and creation of indexes, promoting the shards from replica shards to primary shards that I'll explain. So basically administrative kind of work is done on master node, and its node.data property is basically set to false because the load is not given to that node. That node is responsible for managing it. And to ensure that our master node is stable and it is not under pressure, it is good idea to, in a bigger cluster, to split the roles between dedicated master eligible nodes and dedicated data nodes. And then there are data nodes which will hold only data. So if you want to set a node while starting as a master node, you have to set one property, node.master true. And in one node it will be true, and all other nodes it will be false. And like in a big cluster, there can be multiple nodes for master eligible, because if a master node goes down, what will happen to the entire cluster? Who will manage that? So node.master property is set true to in some of the nodes. Like if master goes down, an master election process is started, and it will come. Okay. किया हाँ start किया pause. Start. So we set multiple nodes as master node equal to true. So when the master node goes down, master election process is there. Let me explain you that how that happens in distributed environments. So what happens there is that using Elasticsearch algorithms, each node finds that which node has a least node value, node ID, and all nodes start sending message to that particular node. And when that particular node finds that it has sufficiently received messages from sufficient nodes, it starts publishing to the cluster. In Elasticsearch, only master node is able to publish states or cluster-wide changes to the cluster. So properties, okay, I have told you that in that node.master should be set to true and node.data should be set to false. So the next one is data node. Data node is basically used for data sensitive operations, like you store your indices on those nodes, and they are CPU intensive, memory intensive, so you need to have more data nodes sufficient enough to handle your traffic. And as your traffic or data increases, you have to add additional nodes. For these nodes, we have node.master set to false, node.data set to true, and there is another property, node.ingest, that should also be false because there are ingest nodes as well. So what do they do? Like we have master for administrative purposes, like we have data for data storing purposes. So if you want to perform some pre-computations on documents, if you are indexing into Elasticsearch, and if you want, it's like a filter kind of thing, like in web terminologies, when a request comes, we filter, intercept them, and we modify it or we do some logging purposes. So ingest nodes are for that. So for example, if you want to remove a field or if you want to add a field while you are storing a document, you can use ingest node for that. They are also dedicated nodes, and if you do not have any such requirements, you don't keep such nodes. It's okay. Node.master is set to false. Node.data is set to false because it is neither master nor data, and its node.ingest property is set to true. And the last one is coordinating node. When a node is nothing, it is coordinating node. Like all three properties are set to false. So it is just used as a what I can say, a good load balancer. It is used for retrieving the requests, and it can forwards the request. It does not hold data. It has no master capabilities. It does not do pipelining. All it does, gets the request, gives it to the different nodes, gather the response, accumulate it, refine it, and then send back to the client. So while we were, okay, later. So the next thing, so this is all about different kinds of nodes in distributed environments. So the next thing is shard. So what actually is shard? So logically, what we can say that they are data containers. They keep our data our data inside a node, there can be multiple shards, and data is stored inside those shards, and those shards are configurable, or they can be defined at the time we are indexing a document. So for example, if I was indexing an employee object, so I wrote like put ibst employee 1. In that JSON, if I'll put number of shards is equal to number of shards, those many shards will be created on the node. And in those shards, that index, that data will be splitted and will be stored in those sites. And we can also give replica sites that I'll show later. So basically, from an end user perspective, shards are data containers, but in essence or in reality, they are Lucene engines. So they are internally, each shard is a Lucene engine or Lucene index, I would say. So as our cluster grows or shrinks, the Elasticsearch there is also a feature now known as migration of shards. These shards are migrated across the nodes. If a node adds up, and if other nodes are heavily loaded, it will move those shards to those other nodes. And that Elasticsearch does. How it does, I have not looked into much into the details, but this is the basic concept, to distribute the load as long as new nodes are added. So basically there are two types of shards, primary shards and replica shards. So the primary shard is the one which holds the original copy of the data. So while we are storing, when we say number of shards is equal to 3 and storing on that node, it will have primary shards. Along with that, we would want our data to be stored on different nodes or different shards as well. So we can also specify a property like number of replicas, and those many shards on different nodes will be used to store the same documents, replica copies. And replica shards are never created on the node on which the primary shards are there, because there's no point. They are replica, they have to be on another node. If this fails, documents can still be retrieved from those nodes. Okay, so now let's understand the cluster states, what happens with the cluster. So when initially without any setting, if I have downloaded a fresh copy of Elasticsearch and if I'm running the Elasticsearch cluster, so it will create a one node cluster, and by default that node is master node. Its master property is set by default true. Now suppose I have my cluster up and running with this one node, and I want to store suppose an employee data, an employee index. I want to index the document. So I can specify how many copies of that data should be stored in shard. So I can write like, while putting, like suppose if I write number of shards is equal to 3. So what it will create create 3 shards, and those 3 shards will be primary shards because I have not specified replica shards. Even if in that request with even if I specify replica shards will not be created, since we have only one node, and primary node cannot, the node which holds primary copy of the data cannot hold replica copies. So now let's add another node to this cluster. So since I assume that I have created an employee index with parameters set number of shards 3, number of replica 1. So with this, what happens? The replica shards will be created. The node will be, when we will boot that node up, we will start that node, it will join the cluster, it will read configurations from the master, and it will replicate shards in its local node. So now our data is distributed. Even if master goes down, we will be able to access our data from data copy which is in P0 from R0, if it is in P1 from R1. So, and now what happens, suppose if we will start another node. So it will, what it will do, to minimize the resource usage, it will start transferring shards from one node to another. So from previous we can see that in node 3 one primary shard has been moved, and from node 2 one replica shard has been moved to balance the nodes, and they are basically done for hardware resources because they should be utilized. So that is done. And now, for example, now let's say when I the one thing is which I forgot to tell you, that when we index a document, we can, at the time of indexing, we can provide primary shards, number of shards, and that is fixed. Once you have done this, you cannot change primary shards, but the number of replica shards can be changed at any time at runtime. And now suppose if I change the number of replicas to 1, so what will happen? So this P1, it was P0. Suppose let's start from P0. In the previous slide, we have P0 and P1. Okay. So in this side, we have added another replica. It has been added to node 2 for R0, and node 1 had also another replica has been added. Node 2 had already R0. Node 1 has been added a replica. And for all these three things, we have added one replica to each of the nodes. So we can increase them. Now suppose if master node goes down at this point of moment, what happens? So let's see next slide. So whenever the master node goes down, and it works on like a heartbeat kind of thing, like they keep on sending messages from master, receiving messages, so they master is alive or not. And the moment nodes realize that master is no longer alive, so they start this master election process in which they calculate the value, they send ping to those nodes, and once that eligible node, with the least node value, node ID value, receives sufficient sufficient requests, ping requests from nodes, it promotes itself as master and starts publishing the cluster state. So new master is created. And the second thing, if you will consider, is that it has promoted these. Look at the R2 in node 2, and this has promoted the R2 replica shard as a primary shard. So this can be done. If there is no primary shard, it can be promoted. So primary shards should always be there. If a master goes down and new master is elected, so first it finds that for a particular index, if there is no primary shards, create one, promote one replica shard to that. So this is the cluster states. And the important thing, and I think interesting, is how distributed search works. Like we see it as a single system, and we give it a search request, and it gives us a response. But what all gets involved into that? So it is basically done in two phases. Any node on which, like how we connect to cluster, we have suppose 200 nodes. We don't give 200 names. We have only one or two names. One name in that app you have shown that I had one address. So whatever address we have kept on that node, and we fire the query search request. Request will go to that node, and that node, it's the responsibility of receiver node to start acting as a coordinator node. So what it does, it gets the query, and it knows that these many shards are containing primary and replica copies of the indices for which search request has come, because in search request we mention indices. So it broadcasts query to all those replica and primary shards and so if you can see the request first number is request has arrived, it has broadcasted those things. And what do? They perform the search locally on their Lucene engine, and they make a priority queue. Like if documents matches, they maintain a list like doc ID, and score, how well they have matched. So this priority queue, which is ordered by descending on priority of relevance, this is maintained locally at each node. And before sending the request, the coordinating node also makes a priority queue, and that is empty by default. So when search is completed, all the nodes send data to this coordinating node, and it merges those queue into that node. So in the second phase, the query phase is also known as scatter phase. The data is search request is scattered, and the next phase is fetch phase. Now you have to fetch. So fetch phase is known as gather phase. In this, what happens? The request has gone, and now they have replied with doc IDs to this node 3 coordinating nodes. Now node 3 will also have parameters like from where to where I have to fetch documents. In search request we mention, or based on that, what it does, it sorts those doc IDs, and from for example, it has got 100 doc IDs, and we have given like from 90 to 10. So what it does, if it will discard those 90 IDs first, And for those 10 IDs, it will make again request to those nodes from which we had received those doc IDs, and then those nodes will prepare those JSON documents of documents, actual documents, not IDs, and then those documents will be sent to this node. And for this, it uses internally a multi-get request. It is also a feature of Elasticsearch, which I did not show you, but it is there as an API, like in series of bulk APIs. So once it has received those documents, it formats the response and then it sends back to the client. So this is how this all happens. And let me cover one point which is not there in slide, which I wanted to share, like how it manages concurrency. Like in application, when you have single application running on single instance, so it's very easy to manage concurrency. You know this part of data will be accessed by several threads. You will put, for example, in Java, we'll make method as synchronized, or we will write a synchronized code block. So this is one kind of application level of synchronization to handle concurrency. The other level of synchronization is in databases, like when we query or when we try to update, we either lock a table, either lock a row, or make a lock on particular record. So how does Elasticsearch do? Because it has several nodes, and one query will go to that node, one query will go to that node. Like think simultaneously, multiple people are trying to update a document. So there are chances of getting chaos. The document will be updated, and it might get overridden. So the approach to deal with this is what they say is the optimistic concurrency control. Uh, what I can say, approach. So in that, what they say, whenever an update or insert or kind of tempering is done to the data, they increase the version number. So it's all versioned in Elasticsearch. Whenever you do something, you saw that when I did that put employee 1, it showed me version 7. So whenever I do any update, it versions up those. So for example, if 2 requests are coming, and for example, right now it's a version like 3 of a particular document, and I'm trying to update. Both are updated, both get the data as version 3, and now suppose it has updated, and the version has been set to 4. Now it has 3 versions, second request has. So when it will try to update, or that request will goes to the cluster, it will find that now the current version has been incremented to 4. So it will send a failure response, and that is left to the applications how they can handle it. The response will be sent as like 409 conflicting kind of thing. The version has been incremented. So that's how it does manages the concurrency stuff. So it is left to the application how they can they might want to redo that operation, or they might want to say some user-friendly messages to the user, but that is left to the application. So the way of handling this is like optimistic concurrency controls. And one thing, okay. Okay, so I think I have completed almost everything. Thank you, guys. So if you have any questions, you can ask. I will try to answer with the best possible knowledge I have. Or if you don't have, we can disperse. Yeah, it's a document-oriented database. Like I said, it treats everything as documents. Yeah. Yes, it is for searching and analysis, like multiple kinds of aggregation. It has different use cases, like what you can say. One of my friend, which is working for a company, they use LogStash product from this. The entire product is known as ELK stack, Elasticsearch, LogStash, and Kibana is a popular stack. From that, they use LogStash. It can be used to verify logs, to find trends, patterns, statistics, everything. It has a visualization tool which can let you visualize your data, like, and you can perform aggregations and all that, which you can do, which we did here. And based on those aggregation, you can have charts, pictorial representation to understand it. So it is heavily used in industry, and unusual patterns can also be found, like it has in its matrix kind, in its one kind of aggregations, we can find significant patterns, insignificant patterns, unusual patterns can also be found. So there is a lot more to its API, but that needs exploration, and I have explored I think pretty common ones, for demonstration purposes, but it is very rich, very rich. You can do almost all kind of aggregations and data manipulations, I would say. Basically, it is used for searching, analysis, and they recommend, what they say, it should not be used as a primary databases because updates are costly in this Elasticsearch. When you update in a distributed environment, they are costly. So mostly people use this as in a hybrid approach, like RDBMS is there, and those data items which are not frequently changed are pushed to Elasticsearch and they are searched from there. And less frequent data items can also be there, but data which is changing very frequently should not be indexed in Elasticsearch. That is the rule of thumb. Okay. MongoDB is, yeah, MongoDB.
If I am taking that data as a primary database, or
you can do.
I can, if I am installing Elasticsearch on that same database, you are not recommending that, or are you saying
No. I am saying that it should not be stored as a primary data source. Like you don't use MongoDB and you are storing everything into Elasticsearch. That should not be done. You can use in accordance with simultaneously hybrid approach with MongoDB or RDBMS. It has some very nice plugins, like it has River plugin is there. The person who did that migration of Wikipedia's data into Elasticsearch cluster, how he did that? It has the plugins are there. Several plugins are there for data migration. You can put data from, you can take data from any of the sources like RDBMS or NoSQL databases, and you can put it into Elasticsearch using that concept. Some configurations are required, which right now I'm not aware of. I have not gone into much detail into that. So, but there are plugins, and anything else?
Elasticsearch is basically looks like handy to use, but free or?
Yes, it is free, open source. You don't have to purchase it. There are no licenses, open source licenses. So that's why this is used heavily in industries, no?
Each replica is stored locally on the each and every.
No, you define. I mean, the node selection process is internal to Elasticsearch.
That I can define that I need
right.
Two replica of this data. It replicates to two nodes extra. It stores locally on that node.
Yeah, stores locally on that node. Yeah. Physical or virtual machines you have like in search. Yes. There are. I have not looked into that, but there might be the plugins like that. Like, yeah, process. But what I will tell you that I watched one video on YouTube from Shah Benin, the creator. What is that people earlier people what used to do, the primarily focus was on storing data. Nobody was involved or was thinking about how well we can retrieve or search that data. So the main concern behind creating this Elasticsearch is I want to search my data, I want to ask questions to my data with any possible combinations, and the physical structure and storage should not restrict me from that. It should be flexible enough to query in enormous number of permutations and combinations. That is the concept of Elasticsearch. Yeah.
For managing the data.
Yeah, managing. So that he told.
They are not
primarily. Yeah.
on the searching part.
They are basically on processing part. I would say. I think MapReduce and other things are there. Computations for there. Yeah. Yes. Yes. That is right. That is right. Sorry?
Natural language processing.
I have less idea. I don't know right now.
So basically, I think that if the node and replica is there, so they are not in the same machine.
Yeah. Node and replica, they will always be on different machines. They won't be on the same machine. Charts. Okay. Any further questions? Thank you.